The proposition is, it has to do with the acronym you heard several times today, NISQ, N-I-S-Q, Noisy Intermediate Scale Quantum. You know we are in the NISQ era right now. And so the proposition for the village is, this village believes that the current state of NISQ is already enabling quantum advantage for those who know how to use these technologies. Arguing for, for the proposition is Rafal Janik.
I got the way around.
Other way around, sorry. Konstantinos, you're arguing for the proposition. Raf, you're arguing against the proposition. And I wanted to say this is so very important because we heard from both of them earlier today. You both know they know their stuff, and it is going to help us come to our conclusion. So first, for the proposition, Konstantinos.
If you like, we can switch halfway.
Yeah, sure.
Show off.
So, do we... Things are happening. Okay. Do we need fault-tolerant quantum computing to do anything useful? I don't think so. If there's one thing I've learned in this decade of quantum that I've been messing around, we get surprised all the time. So just real high level, first of all, we constantly are getting surprised. We find little performance edges here and there, little clever ways to do things like hybrid, where some of it's classical, some of it's quantum, and you put the two together and you see some kind of like performance edge. So I'm not going to worry too much about like provable, benchmarkable advantage so much as like, can you identify some step in a process that could be improved with quantum over classical? So I think we can, and I've already seen signs of it. Recently, IBM did their error mitigation. So they were able to show that basically you were able to cancel out some noise by doing lots of runs and statistically removing it, kind of accounting for it, just to keep it real simple. So it's error mitigation, but there's also error suppression, where you can understand how a particular machine works, and then, for example, you can go through and flip something to reverse an error before it starts to form. Just keeping it super simple. So these kinds of things could already show some benefit, and they did in the case of the IBM paper. So when you look at all those kinds of things, you're going to start to see some provable, I guess what I like to call like customer advantage. You know, it's like when you look at everything and you apply it, you kind of get some kind of edge. I wrote a paper on doing portfolio optimization with cardinality constraints, and we were able to show some performance gain using D-Wave's hybrid solver and some approaches. So yeah, it's not benchmarkable advantage. I'm not claiming that from the rooftops, but we were able to show some gain to that customer. So I do think when you consider all those things, we're getting close. And one last thing I'll add, Quantinuum recently, they did that whole thing with 3, we'll call them logical in quotes, qubits that were able to simulate the energy states of an H2 molecule. So we're getting there. We're approaching. We're knocking on the door. So I think these little tweaks along the way will enable it.
Awesome. Your rebuttal, or your argument against.
I feel a little bit underprepared without memes on the screen behind me right now. So quantum computing has a lot of promise, and it's actually a really hard path to get there. Not only do I not believe that we're at the position right now where we're delivering on that promise, I like to add that it's actually a distraction from the hard work that we have to do to focus on the NISQ era. And there are a couple definitions to cover. The first one is quantum advantage. This is not being able to do something better than a classical computer. This is being able to do a meaningful task better than a classical computer. If anyone's curious, today while sitting over there preparing for this debate, I did a quick search and I found 41 instances of people claiming quantum advantage over the last 20 years. All of those have not come true. And they really fall down for 2 reasons. One, they're flat out fraudulent, which is probably the bulk of them. The other one comes down to the fact that classical algorithms are incredibly good. And many quantum researchers are not classical algo researchers. So what you actually see, and historically we've seen this with multiple companies, is a claim of quantum advantage, and 2 days later, a proof that there's a classical method that is far better. Also, there's a lot of value in quantum computing today. I don't want to discount that. There's the value of what we're doing scientifically and all the research it's been able to unlock. There's the value around quantum adjacent technologies such as, we've heard quantum inspired algorithms. All these are delivering value. But the one thing we have not seen is quantum advantage. And you would not believe how many companies, how many academic institutions, how many researchers only care about running on NISQ right now because they're able to run on hardware. Instead of thinking, how do we prepare for the hardware that's going to be here 5 years, 10 years from now, moving past the NISQ era, not necessarily into fault tolerant, but maybe to non-noisy intermediate scale quantum computers that have gate fidelities and qubit fidelities that actually allow us to go deep enough in algorithms to show meaningful value.
Great, we have 10 minutes for rebuttals. So your first rebuttal, Konstantinos.
Yeah, well, I mean, I don't disagree with anything you said technically, so I don't know if I'm setting this off. It's all good. I just think that we're not, I wasn't bringing up any examples, obviously, of the advantage claims that were useless. I hate that. It's like, look, we did this thing that you're never going to do, but we did it better. It's like, okay, cool. It's just like I don't like when someone writes code and then hacks it. That's kind of useless too. Like what happened with Crystal's Kyber. You don't want to like write your implementation and hack it. That's a little weird. So yeah, that was like the most annoying thing that happened all year. So I agree in that space, and that's why I got big time into quantum inspired. That's why Tensor Networks were hoping to see some gains there. But I keep seeing that hybrid thing, and I can't let it go. I just get this feeling that we're going to be able to take advantage of some of those hybrid learnings and apply them in the work stream. Because like very few problems are solved in one step, one thing. Like supply chain issues, there's like a million places where you could try and improve something. So I just have a feeling in my gut that we're going to see the ability to tweak just a few of those the right way, and like we're sort of like knocking on the door of that. And then there's also the machine technologies that are evolving so fast. So I just go into them for a second, like neutral atom, for example. Talking high qubit counts, really long lifetimes. Like we're expecting the next generation of neutral atom machines that are coming out within a year or so to have lifetimes of like, I don't know, entanglement times of 10 seconds or so. 10 seconds is like, the age of the universe practically when you're thinking about a quantum computer, So if we have an entanglement time of 10 seconds, it makes things a little more interesting. Right now they're running what's called analog mode, which is like not quite, you can't run gates on them, so it's a little closer to annealing than it is to gate, but they will be running gates. And they're going to have modes where you're going to be able to sacrifice a few extra qubits to get like better fidelity when needed. So whenever you think about those like out of the box approaches, I just have a feeling we're gonna see like at least a few of the problems show like some kind of advantage relatively soon, without true fault tolerance across the board.
Great, Rob, your rebuttal.
I mean, this might get into weird debate because we're going to start agreeing with each other more than disagreeing. But I'd like to point out a few things that were brought up a moment ago. Longer lifetimes, better fidelities. This actually pushes us out of the NISQ era. Everything that we're talking about doing, that we want to do, requires much longer lifetimes, much better fidelities. We know a handful of algorithms, and you can count them on one hand today, that can prove quantum advantage. That's a little bit worrying. Instead of worrying about which optimization problem can we try to jam onto a processor today, we should be worrying about how do we actually expand the number of algos that can provide quantum advantage in the future. Maybe even a little more scary than that is the fact that only one of those provides exponential advantage. And there's been papers out of Google AI in the past that demonstrate, even with fault tolerance, quadratic advantage might not be enough. The overheads to build a quantum computer, the way that you actually perform the error correction, might require much higher speedups than quadratic in order to actually overcome the overhead. So I would encourage everyone, again, to not worry about jamming your algo today, your H2 molecule, which you can simulate on your laptop and calculate the ground state on without needing a quantum computer. But actually start focusing on understanding how do you improve the readout method for a quantum computer beyond quantum phase estimation, which pretty much every quantum chemistry algo is based on today.
Great. We have a few more minutes for rebuttals, but those of you just coming in, I want you to know what we're debating is the state of current quantum computers, and if the state of current quantum computers is good enough to give advantage, a real strategic advantage to those who really know the technology. We're arguing for and against, and then we're in the middle of our rebuttals. In a few minutes, we'll get to audience questions and answers and inputs. So we have 2 more minutes for final comments before we get to questions and answers.
In keeping with the theme, I agree with everything you said.
Guys.
Yeah, I know. I'm sorry.
We agree but disagree.
Yeah,
we find
but like what you said
Canadians.
about not worrying about doing a thing that you can simulate on your laptop or whatever, the whole point is like the way it was done, right? You know, just like the first time we ran Shor's algorithm, it wasn't that we couldn't do 15 as 5 times 3. I mean, you could do that. It's just the way it was run. So like the fact that we're approaching fault tolerance through these logical qubits, that we're doing things like error suppression and mitigation. Like these are like the building blocks. So I just view them as incredibly important for that purpose. Even if we could still run the math on a classical machine, I feel like without those building blocks being proven, we're not going to get far enough fast enough. Yeah, so that's why.
I actually like the Shor example quite a bit. So I think I had the mean up earlier, which was factoring 15 into its primes versus the promise of Shor's. When Shor's first came out, the implementation actually would never run on a physical quantum computer with any imperfections. You needed the idealistic machine. And what I would say has been much more important to the development of actually running Shor's has been the work done from the top down, bringing the overheads required for Shor's down, instead of worrying about, can you demonstrate factoring 15 on a quantum computer? It's, again, a great flex, I would say, to do that and to show that, but it's not doing actual meaningful work. I'll add one final point that can probably prove that there's no real quantum advantage, and it's the fact that the people like myself and the folks from Oxford Quantum Circuits are not locked away in a basement right now, working for whichever government that they happen to be under the control of. Because that really will happen as we get closer and closer to true quantum advantage, because the regulations just haven't caught up to where the technology is headed.
Yeah, I was just thinking they're going to steal the machines. I didn't want them to steal you guys too.
I think we go with them. There's no separating the two.
That's terrible.
And to be fair, it won't be me, but those 2 guys are definitely in trouble.
Yeah, yeah. I know there's no true quantum advantage right now because everyone would know about it. Like it would be, big news. But I do believe that we're going to have actual usable use cases. Like I just think we're going to have them before we're proclaiming true fault tolerant, intense gate depths and things. So, and then watch out for those oddball developments, right? Like every once in a while, one of them's going to come true. Maybe not that Chinese paper that you need 327 qubits to crack, RSA. Maybe not that one, but something like that might happen too. That's the one thing I just want to remind you of. Like these surprises they're just things we never would have thought of years ago. I keep seeing things. I'm like, I didn't see that coming. Cool. So that's one of the greatest things about working in quantum.
Thanks, and now it's time to transition to your inputs before we vote. You get an opportunity to ask questions, make comments, push back, make your own arguments, and then we will vote on the proposition. I saw yours first, please, sir.
Yeah. So what do you think is holding up the development of those quantum algorithms? Is it that we don't have the right people trying to build the quantum algorithms right now, or that we're lacking hardware to play around with to validate those, the simulation capabilities? What are your thoughts?
All right, just to repeat the question, it is what do you think is holding up the development of these quantum capabilities? Both of you, please.
Sure. I think broadly, I would say tooling. And I know it might be a very simple answer, but it actually encompasses quite a bit. Somebody mentioned it's like being in the 1940s right now, quantum technology. I'd say that's generous where we are. We're hoping we're going to move more quickly compared to digital computing. But it really is like, before the development of digital computing, trying to come up with potential algorithms. We don't have the software tooling to allow researchers to do what they need to do. We don't have the hardware tooling for them to be able to test it out. And unfortunately, we also don't have the person power in order to actually go after this very aggressively. I'll plug a little bit of the work that the team at the company I work at did in Xanadu. Looking at the simulation of batteries, again, not on today's computers, but in ones that might exist in a decade or in 5 years from now, they reduced the gate count by a factor of 40,000, right? And this is, I would say, low-hanging fruit. They might disagree, it was a lot of hard work. But these are the type of gains that we can make. Unfortunately, the total gate count that you need is still a ways away, but we should be pushing that from the top down as we push the hardware from the bottom up until they finally converge in some place where we can deliver something meaningful.
Yeah, some of this is theoretical, right? If you think about it, the greatest algorithms of all time were developed without a quantum computer, right? They just work. You go right back to the very first one.
The two.
Yeah, the two. Well, they're still the greatest of all time, in my opinion. So they were 1994, 1996. We had nothing. They were just a dream. So I do think in some level it's going to be ingenuity, and it might not even be human ingenuity, right? Like for all we know, we'll get sparks of AGI in a quantum vein. You'll be like, hey, insert name of LLM you love, write me a new quantum algorithm, and it might be possible. So there's that too. It might not be us, or AGI might solve some of the engineering hurdles we have to face. Not to turn this into a whole LLM discussion, but just because of what I've seen with working with tensor networks and compressing them, I think there's a lot more potential there that can be tapped. So I would like to see that. So I think what we're missing is also that we're just limiting it to human beings, and it might be one of our friends. Before they kill us, they might help us. So.
Great. There's a comment here, please.
So in your definition of quantum advantage, you mentioned meaningful tasks, and you also mentioned, I heard throw around real strategic advantage and something meaningful. I want to know what were the benchmarks and the measurements that determine what a meaningful task is, rather than these terms kind of sounding like they are shrouding subjectivity.
Good question about what is a meaningful task in your mind.
I can tell you what not a meaningful task is, and it's an achievement I'm very proud of that, again, Google demonstrated first, but we were able to achieve at Xanadu, which is something called quantum supremacy or quantum computational advantage. And this is cherry picking a mathematical task that a quantum computer is really good at, but classical computers are very bad at, but that you can demonstrate mathematically from first principles that you've done with a quantum computer, and it would take you millions of years, hundreds of years, whatever it is, but much longer with all the computational power in the world to deliver. And this has been demonstrated now 5 times, I believe, maybe 4 times.
Kind of did it twice.
Right, on an optical, on a photonic, and a superconducting computer. Great engineering milestones. Whether they're necessary to get to where you're going, it depends on your roadmap. Now, quantum advantage, it's not a very well-defined term. In fact, none of these terms are. They kind of exist out in the zeitgeist. But what I would say is, it comes down to money. If it's something that somebody is willing to pay you for, and somebody doesn't show up the next day and say, I could do this faster classically. So let me rephrase that. If somebody who is well-informed is willing to pay you for it, then it's real quantum advantage. And very honestly, it's not something we've seen yet from any quantum company, unless they've achieved it and have been incredibly secret about it.
Yeah. So with quantum advantage, right, it has to be useful. Right? It's moving the goalpost argument. So sometimes some scientists don't like it because they're like, no, if quantum could do better than classical, that's advantage. But again, is it a useless problem? Are you just inventing a hamster running in a wheel for no purpose, and quantum can run faster? It's kind of useless, right? So that's sort of what we've had so far, unfortunately. To get some of the advantage like I'm talking about, we've had to do other things too. Like I talked about tensor networks before. We've used those to compress neural networks and then layer them in, and et cetera. You get some other little bits of advantage along the way, and then you get your performance increases. But yeah, I can't claim we have quantum advantage now. No way. Absolutely not.
Can I add one thing? Sure. one thing to be careful of when you see these claims, often people will say this can't be simulated as a claim to prove the power of a quantum computer. But we can't simulate on a quantum level this table, right? But we don't have the control over it to actually make it do anything useful. So a lot of claims kind of fall short when it comes to the hardware. I think somebody mentioned large-scale entangling coming out of China of a number of qubits that if they are fully entangled,
51.
yeah, it's very impressive. But now the next question that needs to be asked, can they exert full control over those 51 qubits to actually do something useful? Because if they can't, then, I mean, it comes down to the thing that I can point to. Look at my 5 million entangled qubits. Don't worry for how long they're entangled or whether I can control them or not, but they're right here.
Pretty sure if you had 5 million entangled qubits, doesn't matter how long.
I
I
know,
think
right
you
here
could do
somewhere.
something.
I'm sure they're here.
Yeah.
There's
5 million qubits
5
could fit
million.
here. That's good. Okay.
Right. Questions? Yes, here, please.
Basic question here, and pardon me if you've already covered this, I came a little late, but what are the consequences of reaching quantum tech? I mean, you know, everybody talks about the advantages we have once we reach that stage, right, of using it, maybe commercializing it or something. But what are the consequences, the cold hard truth of what it could do to live in a world with quantum tech? Also, to the gentleman on the right, did anybody tell you you look like Sheldon from the Big Bang Theory?
It's way cooler.
All right, the question is,
Yeah, I've been accused of talking like people don't understand what I'm saying, but
all right, so the question, to repeat the question, is about what happens when we reach this state of a significant quantum advantage. Right?
yeah. So a couple things will happen, right? If we have advantage and a large enough scale machine, we're at DEF CON, so there's the obvious thing that's going to happen. You know, major cryptographic problems, and that all begins next year, by the way. NIST is going to publish its new standards. So starting next year, that's when the quantum apocalypse begins, because you have to start fixing it. Once the government says this is deprecated, you got to fix it, whether you believe in quantum computers or not. You know, so the apocalypse is here anyway. So that's going to happen one way or another if you're the person fixing this stuff. But the other thing that'll happen is we're going to start solving problems that we never thought we could solve before. I think they're going to use less energy. You know, like even though you imagine these refrigerators and all that, still, quantum computer does a whole lot in a very quick period of time with very little actual energy being expended. So that's the amazing thing that's going to happen. We're going to have these like huge problems being solved that we were never able to tackle before. Things may be involved in the climate. You know, modeling chemicals that can take carbon out of the air. We don't know. It's like the use cases are almost unlimited when you get to that level. So it's a really exciting thing to look forward to. You know, so
Is it scary?
no, because I think we're going to start preparing for the cryptography. And by, you know, like Chrome is about to add in version 116. They're about to add their hybrid post-quantum to that. They've already had it in AWS. So these things are happening already. So I think if we get ahead of it, it'll be like with Y2K. Nothing happened. You know, like it was like, oh crap, it's okay. So it might be fine.
Are you sure?
That nothing happened?
Pretty sure.
There are a couple applications that people think will come first. It was mentioned, quantum chemistry. So basically, one thing that a quantum computer is most likely good at, and again, we don't really know this until we're able to actually run it and prove it, but it's at simulating quantum systems. So this means things like, you know, building better batteries, because now you can simulate all the different electrolytes you would want to without actually have to go through and manufacture a battery. It was mentioned the climate impact. So this is usually around catalysts, usually based around transition metals that are very hard to simulate on a quantum level right now using traditional methods, but would require a modest, still a ridiculous compared to NISQ, but a modest for a fault-tolerant quantum computer number of qubits in order to actually be able to tackle it. But I'd say we don't know. It's like sitting in, you know, 1920 and saying, hey, what are we going to do with digital computers? I don't think we have any idea what like the equivalent of the quantum Tinder application is going to be. It's going to take, you know, a good amount of time to get there.
It'll have a lot of bots though.
We have time for a few more questions before we vote on the proposition that they have been debating on this issue of quantum compute today. Is there any advantage by really knowing them? So here, please, first, and then we'll come back to you.
Do you what is your perspective on the investment of the relationship of quantum and quantum technology as a whole, including computing, and energy as resources dwindle for building batteries and building computers in general? Do you see investment? How do you see that investment happening?
Discuss, please, the investment and the opportunity between energy and quantum.
Sure. So, from the energy perspective, as already mentioned, quantum computers don't operate faster than classical computers. They don't process everything in parallel. The best example is leveraging quantum mechanics. You can essentially encode your problem on your very hard problem on a very complicated system and control it to get the answer out. So you're sidestepping the difficult calculation. And by difficult, I mean completely untractable by classical computation. And this is what all algorithms, quantum algorithms, are based on. So the hope is huge. The hope for, resource scarcity is really massive, and it comes down to anything from optimization work to quantum chemistry to developing small molecule pharmaceuticals, and then all the way beyond that. Maybe if I understood your second part of the question was, like, what is the impact of manufacturing these things? Like, these things actually need to be made out of different materials. It really depends on the modality. Some things are really straightforward. They're silicon-based. There's, no real super rare components to it. Other ones are based on much more scarce things. But I would say the impact that they will have is going to be so much greater than the resources that they're going to consume compared to what classical computers are able to do today.
And some of them could be made with like literally nothing. I mean, ions they're free, they're everywhere. You don't have to make them, they're already there.
I don't know about yttrium, just flowing
Ytterbium,
around.
whatever. Yeah, you just pick them out of the air. There's some in here, I promise you there's some in here. I'm gonna find it when we're done. I'll show you. It'll glow in my hand.
Still not the weirdest thing at DEF CON.
So it depends, like you said, on the modality, what they're made of. And we're already using quantum computers in like simple optimization things for like how to wrap power, things like that. So these are like hybrid problems we're trying to solve using some annealing and some other steps, and tensorizing, whatever. So we're very concerned with like applying this to power in general, because we got a huge problem.
Thank you.
One more question, then we vote.
In terms of academia, let me just give you a 20 seconds context. ACM, IEEE, AAAI, computer science curricula is the project that they're working for the next 10 years, curricula. They're identified 18 knowledge areas, algorithms, operating systems, HCI, all the way to SEP, which is society, ethics, and professionalism. And we're in DEF CON, we care about cyber, but at the same time, you're talking about green technologies and other aspects that quantum will have a big impact for the next 10 years. I was a little bit disappointed that the curriculum guidelines, they only have like less than 2% of learning outcomes and competencies in quantum. However, they're there. But for example, cybersecurity is infused in the 18 knowledge areas. If I will ask you, and this is the question, if I ask you what would be the top three computing areas that you should focus curriculum, like heavily curriculum, what would those be in your experience?
All right, what are the top three curriculum that you would focus on for computer science?
Education. Yeah.
For computer science education overall?
I would say it's pretty straightforward for me. It would be building better quantum systems, writing better quantum algorithms, and absolutely machine learning too, because it intersects so much. So those are the three for me.
I'm going to say the same way, but different. Linear algebra, and linear algebra.
Yeah, man,
Well,
you don't get
spicy
quantum
linear
without
algebra.
that. Yeah, of course. That's like saying you need the alphabet before you write something. 100%. 100%. I tried so hard to like keep linear algebra to a minimum when I talked before.
Thanks. Yeah.
Ladies and gentlemen, it's time to vote. So what I want to do is I'm going to say the proposition again, and then we will ask you to raise your hands if you support the proposition based on the arguments that you just heard. We are in the era of noisy intermediate scale quantum NISQ. This is the NISQ era. NISQ and the future of quantum advantage. This village believes the current state of NISQ is already enabling quantum advantage for those who know how to use these technologies. If you support that, raise your hand.
It's worded that way. I don't think it's already.
If you
I
do
think
not
that we can
support
get
the
there
motion,
without
raise
fault
your
tolerance.
hand.
That's the version I have. Yeah.
There's a lot of undecided.
Yeah. If I could rephrase it, I would say that we don't need fault tolerant for advantage, but I'm not saying we have advantage now, for sure. That's how I feel.
Mark, how did that vote go, do you think?
Oh, definitely against.
All right.
Thank you for the 3 people who are reliably sort of going, yeah, sure.
We have captured this. I know there were a lot of other questions, so please, again, join our Discord server and keep asking your questions there. And with that, I want to say thanks to our debaters for arguing this. Thanks, Mark.
Thank you.